Hello everyone, I'm Siddharthan. This is the fourth deep learning project video in our channel, and in this video we will be working on the CIFAR10 object recognition dataset. So this CIFAR10 data basically contains around 60,000 images of shape 32 into 32 pixel images. So there are 10 different classes. So all these images belong to these 10 categories such as airplane, automobile, bird, cat, etc. So this is basically image recognition problem. So we have to use a convolutional based model, and in this case we will train a neural network, a basic neural network with this data, and later we will use a ResNet50 model, which is a pre-trained convolutional neural network model, and we try to train that pre-trained model with this CIFAR10 dataset. So this is what we are going to discuss in this particular video, and let's get started. So I've just like loaded this data set here, and I'll tell you how you can do this. So make sure you're in the collab environment, and before connecting your systems, go to this runtime option. So in this runtime option you will find this setting for change runtime type, and in this change runtime type you have to give GPU. So in default it will be none. That means you wouldn't be having any GPU provisions. So click this GPU and click save. So this will reconnect your system. That means once this is connected you have access to GPU. Okay, so the reason we are doing this is it will take a very long time for deep learning models or the neural networks to train, so we use GPU in order to fasten this training process. Okay, so that's the purpose. So that will be the first step. Next is we have to import this dataset from Kaggle. So we are not going to download this data because this is a pretty large file. So you can see the size. So it's like around 750 MB. So we are not going to download this. So instead we are going to download this data directly to Collab using this API. Okay, so I hope that you are sure how to import this data from Kaggle, but I'll just explain you this process quickly. So first we have to make sure that this Kaggle library is installed. So this is the code to run this Kaggle library. So in collab environment Kaggle library will be installed, and then you have to the next step is like you have to accept the competition rules. So we have this, just go to Google and search Kaggle CIFAR10 dataset. So this is the site. So it's www.kaggle.com CIFAR10. So in this, so you can see the link here. So competition CIFAR10. So here if you will be having some option to accept competition rules, so somewhere here. So once you do this, in the next step only you have to download your kaggle.json file, which basically contains your account informations. So for that, in this top right corner in this account settings, so click here and go to this account. So in this account, once you have accepted the competition rules, scroll below and give this create new API token. So this will download a kaggle.json file. So once this JSON file is downloaded, you have to come back here and upload this file. So once you have downloaded this file, so come to this files and upload this. So if the name of the file is different, like kaggle 1 2 or something like that, make sure you are renaming this to kaggle.json. So this is very important. So once this step is done, once uploading this kaggle json file is done, so just copy this code and run this. So this is like configuring the path of this kaggle.json, so this doesn't change for any data that you are getting. So run this cell, and once this code is executed, now you have to download this data through API. So this is the API for this particular data set. So this you can find here. So I told you, right? So you have to go to Google and search CIFAR10 dataset. Make sure you have an account in Kaggle, and also make sure you have verified your phone number. So then only you can download this data through this API. So that's a mandatory thing. Now come to this data and scroll below. You will find this option for API. So this is the API for this particular dataset. You can copy this from here. Okay. So once you have copied this, come back to your collab, paste this, but include exclamatory mark before this, and run this. So this will download this 715 MB dataset file. Okay, so once this is done, run this ls. So this ls is a Linux command that we have to print the files or the folders that you have in the current directory. So this is the file that is downloaded, which is cifar10.zip. So this is a compressed file, right? Now we have to extract this file, and for extracting we will use a library called a zip file. So from zip file I'm importing this particular function called a zip file, and I'm giving the path of this dataset. So you can just go to these files, and from this you can copy the path. So this will basically give you this particular path, and again the code is simple, pretty much what I have given here. So I'm reading this file as zip, and I'm extracting this zip file. So extract all, and once this is done, I'm printing the dataset is extracted. That is all. And again I'm giving this ls to see whether this has extracted the files. Now I have this zip file, which is my data set that I have downloaded, and then I have this test.7z, which is my test images, so we won't be needing this for our work as of now. And then I have the train labels.csv, which has all the labels along with the IDs, so we will come back to this later. And then I have this kaggle.json sample submission, so this is basically how we have to submit the results to this kaggle competition. So this is also not necessary for us right now. This is the important file for us, train.7z. So this is another compressed file which basically contains all your training data images. Now, as this is a 7z file, you cannot extract it using this zip file. So for this, I'm installing a different library called as py7zr. So pip install 7zr, make sure you're including this exclamatory mark, so this will download and install this library. So once this library is installed, I'm importing this py7zr, and I'm creating a variable called as archive, and using this 7zip file, I'm mentioning the path of this compressed file. Mode r is nothing but I'm reading this file, archive.extract all and archive.close. So this will extract all the files. So this will basically give you another folder which is nothing but train. So you can also run your ls again to print whether it has like extracted that particular folder, which is this train, right? So this has been extracted. Now if you want to extract this to a specific folder, in that case what you have to do is, so within this parenthesis you will mention a path. So I'll just show you. So I'll make a comment here. So if you, let's say you want to download this to a specific path, so in this extract all, I have to mention a parameter called as path, and let's say let's create a folder. So I'll create a new folder and I'll name this as training data. So training data, and from here I can copy the path. Like you can do this in your local machine as well. So once I copy this, I can like mention this as training data. So make sure you're doing this after creating this training data folder. So this is a empty folder, so all these data will be extracted to this training data. So this is how you can extract this to a specific location, but in this case I'm just extracting it to the default directory that we have. So these are some of the basic things on how you can get access to this data set. So now let's get into the actual part of processing this data and how to build our neural network. So as I've told you, first we will build a very basic neural network, and later we will import a pre-trained model which is ResNet50, and I'll show you how you can train this ResNet50 on top of your custom dataset and build this use case of CIFAR in object recognition. Okay, so the first step that we have here is importing the libraries. So I'll create a text here and I'll mention this as importing the dependencies. Okay, so first I'll import the library OS. So this is basically to run through the different files that we have here, and I'll also import numpy as np, and I want to import pandas for reading this train labels.csv. And next is, let's import some image processing libraries such as pillow. From pil I'm importing image, so I should be caps, and then I'll also import matplotlib image. So import matplotlib.pyplot as plt, and then let's import the module image, matplotlib.image as mpimg, and then let's also include train test split. So from sklearn dot model selection import train test split. Okay, so the next step is going through this training data folder and checking like how many files are there in this particular folder. So I'll create a variable as file names. So this file name is equal to OS. So we have imported this OS, and from this I'm importing this list dir, which stands for list directory. So this will list all the files or the folders that is present in a particular directory, and the directory that I want to check is this train. So I'll go here, copy the path of this train folder and paste it here. Okay, so make sure to put this in quotes, and this will basically give you a list. So if you want, you can also check the type of this file name. So this will tell that this file name is a list because we're creating a list using this function, right? And now you can check the length of this file names. So let's see how many files like images are there. So totally there are 50,000 images. So basically this training data contains 50,000 images with labels that are stored in this train labels.csv, and this test data contains 10,000 images for your evaluation. But for this we won't be having the label, so that is with the people who are like hosting this competition, so we are not like worried about this. So we are going to take this training data and we also have the label. So from this we will split this training data into training data and test data, and then we will do our evaluation for ourselves. So this is the step. So we have 50,000 images for 10 different classes. Okay, and I'll also show you, as I told you, this basically list all the files in this directory. I'll show you some sample of the images that we have. So I'll print file names 0:5. So this will print the first 5 elements in this list, and I'll also print file names of -5 of 0. So this will print the last 5 files in this list. Okay, so you can see, so this is the first file that we have, 7796. These are the first 5 files, and these are the next the last 5 files. Okay, and the next step is to take this train labels.csv and process it such that we could have this labels in a list or a array that is like more suitable for our training. So that will be the next step. So I'll just add a text here as labels processing. Okay, now let's we know that this labels is in the form of a CSV, so let's load this CSV into a pandas data frame. So that's why we have imported the pandas library, and I'll name this as labels df. So labels df is equal to pd.read csv, and within this we have to mention the path. So I'll go here and copy the path of this train labels.csv. So copy the path and paste it here. So now first let's check the number of basically the shape of this data frame. It should tell us 50,000 rows. So let's see. Yes, we can see we have 50,000 rows, which corresponds to the 50,000 training images that we have, and it have 2 columns. So these 2 columns are nothing but your ID and label. So I'll go here and give this labels df dot it. So this will, we know that this will print the first 5 rows in this data frame. So we have 2 columns. So first is your ID. So this is the index. So this is the default one, and then we have this ID and the corresponding label, right? And this ID is nothing but these are the name of your files. So 7796 is nothing but the ID of this particular image, and like in the corresponding value here, like say for example in the 7796 you will have like the corresponding label for this, right? So if you want to see this, I'll just show you. So labels df of labels df ID. So I'm going to mention this particular number, which is 7796.png, right? So I'll 7796. Okay, so let's run this. So this will show this particular row 7796 ID, and it says that this is a frog, right? So similarly these are the IDs, and these IDs are mentioned here in order, and the corresponding labels are given here. But the problem here is the images are not in order, right? In this particular folder we can see that it starts from these ID numbers, and we could see that this is not in order. So that's the next thing that we have to solve. But for now we can see that this is the data frame that we have, and the other main thing that we have to see is whether the IDs are in order in this data frame. So that's important. So let's check this. So here I'll give this labels underscore df dot it, and I'll put 10 here. So this will basically give you the first 10 rows in this data frame, right? So we can see the ID is in order. Let's also check this for the last 10 rows. So that you can do using the df.tail command. So let's run this. So it ends in 50,000. So we can clearly say that all the IDs are in order. So now what we can do is take this ID column as list and pass it to a for loop and read the images in this particular order. So what I'll do is I'll take this ID column in a list, so and I'll iterate my for loop through this list. So first value is 1, and then I'll add this .png to this, and from this folder, this particular folder, which is content.train, I'll read the file that has the name of 1.png and convert it to a numpy array, and then I will read this 2.png and convert it to a numpy array. So this is basically reading the images in order. So that's the idea of this. And the before going to that part of reading the images and all these things, we can't deal with this particular type of labels which is in the form of a string. So I want to convert this to numbers. Say for example, if it is a deer, I want to convert it to 0. If it is a bird, I want to convert it to 1. So I'm just like numerically encoding these values. So there are like two ways to do this. I mean basically three ways to do this. So first step is to manually convert this strings to some numerical values, or you can also use your label encoder. But in this case I'm not going to prefer label encoder because we may not be sure of how the labels are converted. So we may not know how deer is converted, like whether it is converted to 0 or 1. So that we may not be knowing directly. So I'm going to manually convert this. And the other way, the third way, would be the more efficient way of instead of numerically encoding them, will be one not encoding them. But for now, let's not move to one not encoding. So if you want, you can definitely try it. But now I'm just going to encode this with numbers, but I'm going to do this manually. Okay, so let's see. And before just doing that, I just want to make sure that there are only 10 labels and there are no 11 labels as mentioned in this data set. So, and also I want to check how many images are there like in this 10 classes, like how many deer images are there, how many bird images are there. So that I want to do. So just pause this video and think for some time how you can do this. So I hope you would have some idea. So here what I'm going to do is use a data frame function called as value counts. So we have used this value counts multiple times to check the distribution of the classes that we have. So in this case I'm going to use the same thing. So labels df, and within square bracket I'm going to mention the column name, which is my label. So this column, and after this I'm going to say dot value counts parenthesis. Let's see how the distribution is like. As we can see, there are 10 classes, and for each class we have 5,000 images. So the distribution is even. So this is a great thing, because if the distribution is not even, then our model cannot make predictions correctly. So that's the problem. So in this case what we are going to do is take this frog, convert it to 0, take truck, convert it to 1, and so on. So let's take a very simple way of doing this. So I'll complete this code and explain you what I'm doing here. So I'll create a dictionary and I'll name this as labels dictionary, and I'm using this curly brackets. And first uh, if it is an airplane, I can convert it to, so I'll just use the alphabetical order. So first is I have this airplane, right? So airplane should be 0, and let's convert this automobile. So I'll copy from here. So automobile, let's encode this to 1, and then we have bird. So let's convert this bird to 2, and the next label will be your cat. So cat should be encoded to 3, and the next class is deer, and let's encode this deer to 4, and next will be your dog. So dog should be encoded as 5, and then we have frog. You can take any order. In this case I'm just taking the alphabetical order. Again, it's up to you. So frog I'm taking 6, and horse should be 7, ship should be 8, and finally we have truck. So let's have this truck as 9. Okay, so these are the 10 different classes that we have. So airplanes, I'll just count. So this is 1 2 3 4 5 6 7 8 and 10. Okay, 0 1 2 3 4 5 6 7 8 and 9. Okay, so we have 10 elements here. Now we know that dictionary is a key value pair, and the label names are my key and value are basically how I'm going to encode it. So I want to convert airplanes to 0, automobiles to 1, and so on, right? And now I'm going to create a list, and if it is a frog, I will encode it to 6. If it is a truck, I'll basically encode it to 9. So I'm just going to do this using a for loop and with a list. So I'll create a list called as labels. So this labels is equal to labels dictionary of I. This is an interesting way of doing this. So for I in labels df, label. Okay, So let's try to understand what we are doing here. Okay, so I have this for loop. So first let's look at this for loop. So we have this for loop of for I in labels df of labels. So when I say for I in labels of df, so let's print this alone. Let's see what this is giving. So labels df is my basically my data frame, and this is the column that I'm mentioning. So this will give all these values: frog, truck, deer, all these in order. So which order? It's the basically the order of the id, right? And I'm iterating this through this particular column. So when I say for I in labels of df, so when this for loop runs for the first time, it will, this I will take the value frog, right? And this frog, this basically, this is I is frog, right? So this frog will go here, right? So when I say labels dictionary of frog, so this will look into this particular dictionary and see like what is the value for frog. So it is 6, right? So the next time this for loop runs, it will take, I will take the value of truck, and this truck will be passed here, and it will go through this dictionary of what should be the value of truck. So it should be 9. Right? So at each step it will append these numerical labels to this list called as labels, right? So basically we are initiating a empty list, going through this column, and for a particular label we are converting it to the corresponding numbers that is given in this dictionary. So we are doing all these 3 steps in this single line of code. So this is basically how you can create a list with a for loop. Okay, so I'll run this, and let's then check how this encoding is done. Okay, so we have the first 5 basically first 5 labels and the last 5 labels. Let's see whether this labels is encoded correctly. So print labels 0 is to 5, and let's print the last 5 labels, which is 5 column. Okay, so let's see. So frog should be labeled as 6, so it has labeled correctly. And then we have 2 trucks, and trucks should be labeled as 9, so we have 9. And then deer 4, yeah, so automobile is 1, so it has labeled correctly. So the last should be automobile 1, so we have this 1. This is also automobile 1, truck 9. So this labeling has been done correctly. And the main thing is the labels are in the order, like they are in the order of the id, because we know the id starts from this 1 2 3 all the way up to 10. Here it starts with 0 because this is not id, this is the index. So this is nothing but this particular index, so we don't have to look into this. So the main idea, the main thing that we have to understand here is, so it contains 50,000 labels, but the labels are in order of id number from 1 all the way up to 50,000. Now in the same order of 1 to 50,000, we have to read the images that are present in this train folder, right? So that will be the next step. Like if you want, you can open this train folder. Basically it will take some time because it contains around 50,000 images, so you can double click it, so it will display the image. So I'm not going to do this because these images are like really small. So you can see that these are 32 into 32 pixel images, so these images will be really small. So if you want, I'll just show you once like how you can read an image. So for this we can use this cv2 library, which is opencv. So I'll just create a uh, comment as displaying sample image. So here I'll import cv2, and here I'll read this image as img is equal to cv2.imread, and within this I have to pass in the path, right? So the path will be train data folder. So let's copy the path. And after this we know that these are the files in this path, right? So we have 7796, right? So I'll copy this 7796.png. So these are the files in this folder. So I'm not going to open this from here, I'm just copying this from here, right? So put a column, right? And now we want to display this. For displaying in opencv, basically the cv2, we have a function called as cv2.imshow, but that imshow won't work in Google Colab, because basically that imshow will create a window, and in this Colab it's not suitable to create a window. So they have replaced this with their own function, which is from google.colab.patches import cv2 imshow. Okay, so basically what happens here is, when I read this through the cv2im read, this will convert this image to a numpy array, and the cv2im show will convert this numpy array and it will display this in the form of an image. So that's the main idea. So I'll copy the cv2im show, and within this I have to pass the variable image, which is nothing but this image that has been read through cv2. So let's run this. Right, so I think this is a frog, so this is the reason I didn't want to print this, as this is like really small, because we know that the shape is 32,32, right? So you can also try different images, but I'm not sure whether the image will be clear. So we can also cross check this. We have checked this, right? So yeah, so 7796 is frog. It's actually looking like a frog. Now I'll just copy a different image. Again, I'm not sure whether it will display this properly because of the size. So I'll copy this 45888, and let's see if we could see what this image is. Yeah, this seems like a dog. I think so. So we can also, do something like this. So I'll just like confirm this. Yeah. So with this, we just have to replace the ID. So the ID will be 45888. I'll copy this and paste it here. So we are just extracting this label from the data frame, right? Yeah, it is a dog. Like, so similarly, you can just read this image and display it if you want, right? So the next step would be to read these images in order, because we know that the images are not in order in the train folder. So that is the next step. Now what we are going to do is create a list that has values from 1 to 50,000. There are two ways to do this. One is you can basically create a for loop and add values from 1 to 50,000, or rather what you can do is take the values directly from this labels df. So I'll print this labels df once for you. So labels df dot it. So I'll run this. So we have all these things, right? Now I'm going to take this id column alone in a separate list. Okay, so I'll create a variable as id list, and this id list is equal to list of labels df, and in this square quotes I'm going to mention id, right? So I'll show you how this works. So I'll run this, and now I'm going to print the first 5 values and the last 5 values as we are doing before. So 0 to 5, and the next one should be minus 5 of 0. I mean, you can just say minus 5, right? So we have the values from 1 2 3 4 5 all the way up to 49,996, all the way up to basically 50,000. Now I'm going to pass this through a for loop, add .png to all these numbers, and then read the image. So that's what we are going to do, and for this, like, that would be the next step. So let's do this. So this process, I'll put this as image processing. Okay, so here let's say convert images to numpy array, and I mean, we don't want to resize the images, so we are just going to take it from 32,32. Okay, so if you want to resize, you can resize in this particular step itself. So if you have seen my dog versus cat video, I mean, this is it's basically the same step of reading a folder that contains images, resizing them, and storing them as numpy arrays. But in this case, we don't want to resize. Let's have this in 32,32. Okay, and here I'm going to give this as train data folder. So I hope you know what's the training data folder. So it's nothing but this one. Not this is just the sample folder that we have created to show you like how the 7z works. So let it be there. So this is the folder, actual folder. So I'll copy this path and I'll paste it here. Make sure to include forward slash here. So this is very important, because to this path, so this is like the default path. To this path, I'm just going to like put 1.png to this. Like if you don't include this, so what you will get is you will get like 1.png, right? So yeah, so 1.png. I don't want this. I want this to be slash and 1.png. So make sure that after train you are putting a forward slash. And next I'll create a list as data. So now what I'm going to do is take 50,000 images, convert these 50,000 images into 50,000 numpy arrays, and I will enclose all these 50,000 numpy arrays in a list, and this list is nothing but the data, right? And now I'm going to say for id in id list, image is equal to image dot open train folder path plus string of ID uh, plus dot png, right? I think it's better if I show you how this entire thing work. Okay, so let's print this. Okay, first of all, let's try to print this alone for maybe 5 images. So I'll call this as image path. So this is just to show you how this entire concatenation works. Okay, so training data folder string. Okay, now let's print this image path and let's break this. If ID is equal to 5, I just want to break this. Okay, sorry. Right, so this is what we would get. So basically we are taking this content slash string, and then the next step is we are taking this ID. So each time this for loop runs, so this ID will take a new value. So nothing but the values in this ID list. So first time it runs this ID takes this value 1, right? So once this ID takes the value of 1, so we convert this 1 to a string, because then only we can add this dot png, right? So I'm converting this 1 to a string, and then I'm adding this dot png, which is nothing but this part, and later I'm adding this dot png to this train data folder, which is this, right? So at each step you would get this particular path. So once I have this path, I will read the images, convert it to numpy array, and store this in data is equal to this particular list. So that's what we are going to do. So for now I'll remove this. So I hope you are clear with what we are doing here. So for ID in ID list, image is equal to image.open. So this image is nothing but the one that we have imported from pillow library. So I'll just show you quickly. Yeah, so you can see, so from pill we are importing image. So again, this is a very useful library for processing your images. So image is equal to image.open your train data folder, and then as I've told you, we have to convert this string, this ID into a string, because then only we can add this dot png to it. So dot png. So again, so all the images are in the form of dot png. If there are like jpg images, that this won't work. You have to work something in that so that you properly add jpg or png to this. But for now we don't have to worry about this, because all the images are of dot png extension. Okay, so image.open training data folder, converting the string to ID, this string to ID, and then adding .png. So this image.open will read image using this pillow, but it won't convert it to a numpy array. So it will be a different object called as pillow object or something. And now I want to convert this image to a numpy array. So I say np.array image, right? So this image is nothing but this image, right? I'm not changing the variable name. So first we are reading this image, converting to a numpy array, and storing it to the same variable name, and this is the numpy array that I need. And now I'm going to append this to this data list. So data dot append image. Okay, so let's try to understand what's happening here. So this won't change, this training data folder string won't change, and then we have a empty list. So let's say that this for loop runs for the first time. So when I say for ID in list, that means ID is equal to 1. Now image is equal to image.open. So this path plus 1.png. So this image will be read and stored in this image, which is a pillow object, and then we are converting this pillow object to a numpy array, and we are appending to this data. So once this for loop runs for the first time, this data list contains one element, which is numpy array of the first image. When I say first image, it's the numpy array of 1.png. Next time it runs, it converts the image of 2.png and it stores in this list, and this process goes on. So I'll run this. This may take few seconds depending upon the size of your data. So if you want to resize this image just before converting this to numpy array, we can like resize this using pillow. There are like different functions for this, so I mean you can look those things, right? I'll just show you the type of this data. So this should say this is a list. So we have this list, and I'll also check the length of this list to make sure all the images have loaded correctly. 50,000. So I have all these 50,000 images. Now we have to check what is the type of the first element in this list, right? So I'll say type of data of 0. So when I say data of 0, it's the first element in this list called as data, right? So I'm going to check this data. So to make sure that it is in the form of a numpy array. As we can see, it is in the form of numpy.nd array, which is n dimensional array. Now I'm going to check what is the shape of this numpy array. So I'll say data of 0 dot shape 32 comma 32 comma 3. So just take a moment to just think, what is this shape? So why we have this 32 and 32 and why we have this 3? So this is very important. Okay, so I have explained this in my image processing video. So if you want, I'll give a link in this video description. So I have explained you what are all the different types of images, how this image data is converted to this array, and so on. So it's like, it's best if you watch that video if you haven't watched it already. So this 32 is nothing but your height of the image and the width of your image, and this 3 basically represents your color channel. So there are two types of images. One is grayscale image and the other type is a colored image, which we call it as RGB image. So RGB stands for red, green and blue, because all the colors can be made from these three colors. So these three are the base colors, right? So when it is a grayscale image, or basically a black and white image, you won't have any values here. So you will have the shape as 32 comma 32. So basically, if this data set contain the images in the form of black and white, the shape in this case we would have got it as 32 comma 32. That doesn't mean there are no channel. It means that there is only one channel, that is my white and black channel. And when it is a grayscale image, we get this as 3, which is my red, green and blue. So this is really important. We know that this is a colored image, so we get this shape as 3, right? So this is basically, each image can be represented as a 32 comma 32 matrix, basically 332 into 30, 32 into 32 matrix, right? So first matrix corresponds to the red color intensity, second matrix corresponds to green color intensity, and the third matrix corresponds to blue color intensity. So this is the meaning of this 3. So now let's just print this data of 0, right? So it will give you this array and these are the values. Now if you say this, all the values ranges between 0 to 255. Again, I have explained this in that image processing, so you have to watch that. So basically 0 means it is like as I've told you, there are like 3 matrix, right? So if for a first pixel, so if in this first value all the values are 0 in the 3 matrix, if the first value is 0 in the R matrix, G matrix and the blue matrix, that means the color of the pixel is black. If the value is 255 in all the first value, that means the color is white. So similarly, you have all those color combinations and so on. So the main thing that you have to understand here is, when we convert this image to a numpy array, all the values range between 0 and 255. So that's the key thing. Okay. And yeah, so basically we have what we need. So we have 50,000 images. All of these images have been converted to numpy array, and this is the shape. So all these images will be of this shape. And there is other thing, if in this case, they have mentioned that all the images will be of the shape 32 comma 32. There are cases where the images will be of different shape. In that case, you cannot pass that directly to your neural network. You have to make sure that all the images are of same shape, right? It can be any shape, but you have to make sure all the images are of same shape. So that's really important. And so in the next step, what we can do is convert this. We know that this is in the form of a list. This data is a list, and our labels is also in the form of list, this label. So these two are the things that we need to train our neural network. Let's convert this lists to numpy arrays, right? I'm going to rename this to x and y. So let's put a comment here as convert numpy, basically images and labels to numpy arrays. Now it is in the form of list. Okay, let me put this as images list and labels list to numpy arrays. So this is a very simple steps. I'm going to say x is equal to np dot array. So x should be my images, so I'll say data, and we just have to do the same thing, but in this case we have to rename this to y and np dot array labels. I'm just changing the data type, so there is like nothing much going on here, but this is important. So now I'll check the type of x and y. So I'm not going to check for both, I'll just check it for x. So we know that it's a numpy array, and I'll also print the shape of this. Print x dot shape, and let's print y dot shape. So there is some interesting thing that we could see here. 50,000 comma 32 comma 32. So what this means is there are 50,000 numpy arrays or 50,000 images of shape 32 into 32 with 3 color channels. So that's the meaning of this. So this represents the number of data points or the number of images. So this is your height and width, or it can be your width and height. I'm not exactly sure of that particular order, but I think it's height and width. And then you have the color channel. If it is grayscale, you wouldn't be seeing any values here. It means that it is understood that it is 1, it's not 0. So this is important, just keep this in mind. So we have, in this case, we have 50,000, 32, 32 and 3, and this 50,000 is nothing but your y shape. So it basically contains your 50,000 labels. Okay, in the next step we have to perform train test split. Like, I mean, we have been doing this for ages, so we know what is meant by train test split. So we take this 50,000 data, take some data as training data and some data as test data. So train test split, making this bold, and I think I've already imported it. Okay, so x train, x test, y train, and y test. So this order shouldn't change at all. So we have x train, x test, and y train and y test. So this is equal to train test split. So if you remember, we have imported this train test split from sklearn.model selection. Again, this is a very basic thing. So sklearn.model selection, we are importing this train test split, and here we have to pass this x and y. So let's say x comma y, and test size of 0.2. So I'll tell you what this test size means. Random state is equal to 2. Okay, so I always use random state is equal to 2. You can use any number you want. So we are passing this x and y, which are my images and labels. Test size of 0.2 means out of this 50,000, I want 20% of images to be my test data. So you can calculate like how much will be your 20%. So 10% will be your 5,000 and 20% will be your 10,000, I think so. So 20% will be your test data, and the remaining will be your training data. Now random state is again an interesting parameter, but not that much important. So when you run this train test split, it will split the data in a particular order. Like some random images will be your training data, random 40,000 images will be your training data, and the random 10,000 images will be your test data. And if you run it the next time, it won't contain the same images. So there is some kind of a shuffle that's happening. If you want to retain the same order, in that case you will use random state some number. Okay, and the other reason is just to reproduce your code. Let's say that I'm splitting my data in a specific order, and you want to split your data in the same order, then in that case we both have to mention the same number, right? So it's basically for that purpose. So I'll run this. Now my data will be split to training data and test data. Now I'll check the shape. I'll check the shape of x, which is my original data set, and then I'll check the shape of x train, which is my training data images, and I'll also check my test data images. Okay, so this should, yeah, so 50,000. So this won't change the dimensions of the image. So we have to look into the first number. So original data contained 50,000 images, and 80% of this 40,000 will be your training data images, and 10,000 will be your test data images. Okay, and the next is a very important step. Now we are going to scale the data. So this process is, again, it's called as normalization. Basically we are going to scale down the data. So I've mentioned you that the values ranges between 0 to 255, right? Now I'm going to convert these arrays such that I have all the values from 0 to 1. So basically what happens here is, if the value is 0, in that case basically your value will be 0, right? And if your value is 255, in that case your value will be 1, right? So all the zeros will be the same zeros, and 255 will be converted to 1. So we are scaling to this range of 0 and 1. So all the numbers between the 0 and 255 will take the numbers between 0 and 1. Like, we are just scaling down the pixel value. There is like nothing much complicated going on here. So this is done, and in most cases it will increase the performance of our neural network. So this scaling is a very important step that you have to follow. So I'll show you how you can do the scaling. It is a very simple step. So I'll show this. So let's create a comment here as scaling the data, and I'm going to scale this and store this in a different array. So scaling the data, so we have to, I mean, we don't have to scale the labels because it has the values from 0, sorry, yeah, 0 to 9, right? Yeah, I think so. So let me quickly check. So we have 0 to 9, so we are not going to affect this. The only different thing that you can do here is, instead of numerically encoding, you can apply one hot encoding, which will be a more effective way. But in this case, let's go with the normal numerical encoding as we have discussed earlier. Now let's scale this. So I'm creating an array called as xtrain scaled is equal to xtrain divided by 255. Okay, similarly we have to scale our test data. So this will be your x test scaled, so this should be converted to x test, right? So this is the step. Now it's a very interesting thing. You can't do this in a list, but in the case of numpy array, when you divide this numpy array by 255, all these values will be divided by 255, right? So when I do this, if it is 0, it's nothing but 0 divided by 255, so you will get 0. If the value is 255, 255 by 255 is 1. So as I've told you, all the values in between them will lie between 0 and 1, right? So that's the basic idea. So we are basically scaling down it to 0 and 1. So I hope you are clear with this. Again, there is not much complicated in this. So I'll run this. Now I'll print this xtrain scaled, the first image of this for xtrain scaled, right? So you can see all the values are between 0 and 1, like you can go through this. But if you print your xtrain, it won't have those things. Xtrain of 0, right? So we are converting this numpy array to this numpy array, right, by just basically dividing it by 255. So when I do this, so all these values, yeah, so all these values will be divided by 255, and this will happen on all the 50,000 numpy array. So that's what happening here. And yeah, I think that is all. Now we can probably move on to building our neural network. So for this we need libraries like TensorFlow and Keras. So let's work on that. I'll make sure I'm explaining the things simply, so that even if you don't know much about the deep concepts of neural network, you will get to know how to implement this. So that's the main idea for doing these use cases. So I'll create a text as building the neural network. Sorry. So building the neural network. So I'm going to import TensorFlow as TF. So I mean, again, TensorFlow is already installed in Colab, but if you're working on your local machine, if you're working on Jupyter Notebook or Spider or VS Code, you have to install these libraries. And from TensorFlow, import Keras. Now let's just quickly discuss about this TensorFlow and Keras. So TensorFlow is like the base library. So TensorFlow is developed by Google, and there is another famous library called as PyTorch, which is developed by Facebook. So these libraries are used for building our neural networks, and Keras just makes things easier. It helps us to use these libraries in a easier way. So Keras is just like a wrapper. It uses TensorFlow or PyTorch in its backend, but again, we are building the neural networks on TensorFlow or in PyTorch. But Keras just makes things easier. So that's the thing. So if someone asks you what is meant by Keras, you can just say it is a wrapper of the libraries like TensorFlow and PyTorch, which are basically your deep learning libraries in Python. There is another library developed by Microsoft, which is called as CNTK, which stands for Cognitive Toolkit. Okay, so this is the purpose of this library TensorFlow and Keras. And now let's build our simple neural network. And like I'll tell you, the performance will be really low. Later we will be using ResNet50, which will boost the performance of the model. So that's what we'll be doing here. Okay, so I'll first create a variable and I'll call this as number of classes. So here we just have to mention how many classes are there in our data set, which is 10. Right? And now we are going to set up the layers of our neural network. So I'll mention this as setting up the layers of neural network. So I mean, we are not going to add convolutional layers, as this is a very basic one, but this ResNet50 has those convolutional layers in them. So first let's just build a basic network. So if you have a neural network, there are three main layers to it. First is your input layer, and then you have multiple hidden layers. So I mean, you can have any number of hidden layers you want, and finally you have your output layer, which predicts the class that image belongs to. Okay, so I'll create this variable as model, and I'll say model is equal to keras dot sequential. So this process won't change for the neural networks that you build. So keras dot sequential, and within this parenthesis I'm going to open a list. And within this we can mention the different layers that we want. So let's say 1 sec, yeah. So keras dot layers dot flatten. So I'll explain you what's the purpose of this flatten in a moment. So input shape is equal to 32 comma 32 comma 3. Put a comma here, so that's again important. So keras dot layers dot dense. I'm going to take, okay, I'll take 64 neurons, and I'll put this activation as relu, which is rectified linear units. And then I'll add another, basically the output layer, layers dot dense. Here we should put the value as 10, so this value should not change. In this case you can have the number of neurons as 32, 120, 256 or any number, but here the value should be 10 because it's nothing but the number of classes that you have. So again, it's a good practice to put this variable, so in this case to just, so that someone, you know, reading your code understand like what you have done. So instead of putting 10, I prefer, you know, I also suggest you to put this 10 in a variable and putting that variable here so that it is clear. And activation is equal to softmax. So you have different activation functions. So you have relu, as I've told you, which is rectified linear units. You have sigmoid, softmax, and so on. In the output layer, I mean, it's not like the rule, but we generally use sigmoid as the activation layer when it is a binary classification problem, or in other words, you are predicting only two classes. If it is a multi-class classification problem where you have more than two classes, where in this case we have 10 classes, we can preferably use softmax, right? So we have the input layer, which is this flatten, and we have one hidden layer with 64 neurons, and then we have the dense output layer, like the final layer with 10 neurons. So each 10 in this 10 neurons, each neuron correspond to the 10 classes that we have, right? So if the image is a frog, then there is a neuron that is assigned to this frog, so that neuron will give you the highest probability. So we just like look into this probability and find like which class the neural network is saying that this image belong to. Say, like, let's say we are training the model and we are passing a new image to predict which class it belongs to. So we look into this 10 final neurons output, which is basically a probability value, and see like which neuron gives you the highest probability. If the you know, frog neuron, which is the number 6, gives you highest probability, we say that that image is a frog, and this same for the other images, right? Now let's discuss this flatten, and the important parameter that we have to mention is this input shape. Here you just have to mention the shape of your image. If it is a black and white image, we just say 32 comma 32, right? So that 32 is nothing but the shape of the image, as we have seen in this case. Just a moment. As we can see, so if it is a 224 comma 224 image, in that case we change this here. So this is the only thing that changes. Flatten. So what happens in this flatten is, we know that this is a 3 matrix with shape of 32 into 32, and we won't be passing this as a matrix but in the form of a vector are nothing but like it just has a single dimension. So you can think about this as a single column of values. So this is what is done by this flatten. Again, this is a common step in the neural networks that we build. And then we have this hidden layer that has 64 neurons. Activation function, as I've told you, there are different activation functions that we have, and this output layer. And another interesting thing about this hidden layers, so why I've used a 64 is, you can use any numbers. You can, I mean, use 65 or 70 or something, but generally people use values in the power of 2. Like the usual number of neurons that we would have will be 32, 64, 128, 256. It's not that you shouldn't use some other numbers, but like the reason we use these two powers of 2 is it's computationally efficient to maximize the usage of RAM CPU, basically for that purpose. But again, it's not that you have to use this number. Basically your training will be efficient when you use these numbers. So if you have like multiple neurons, we start with a larger number like 256, and in the next layer we will be having 128, and then we'll be having 64, and then 32, so something like this. So in this case I'm just having one hidden layer and I'm having this as 64 neurons. Okay, so let's run the cell. My runtime is disconnected, so let me see. So this will be the step where we are building a neural network, and in the next step we have to compile it with some the optimizers, metrics and other things. So I'll show this to you now. Yeah, so the cells are executed. Okay, so let's run this. So this is just setting up the layer. Now we have to compile this. So compile the neural network. Okay, so I'll say model.compile. So here we have to pass three things. One is your optimizers, which updates your weights. So I'll say optimizer is my Adam optimizer, which is a most commonly used optimizer. And for loss, I'm going to use sparse categorical cross entropy, basically your loss function. Again, so there is another important thing here. So the reason I'm using this sparse categorical cross entropy is I have like numerically encoded labels like 0, 1, 2, 3 and so on, right? So where is this? Yeah, so I have this like numerically encoded ones. If I have one not encoded labels, in this case I can use categorical cross entropy, right? So if you interchanges, it will give you an error. So that's the thing about this. And the next thing that we have to include is your metrics. So for compile we have this laws and metrics, right? Yeah, so metrics should be accuracy, as this is a classification problem. So I'll say metrics is equal to ACC. Okay, I think this, yeah, I think this is sufficient. And now let's train our neural network. So again, this is the usual steps that we have. So first we have to set up the layers and the input shape, all these things for our neural network, compile it with suitable optimizers, laws and metrics, and then we will fit our model. So this step is training the neural network. Okay, and again, so this process will take a long time if you don't change your runtime to GPU. So that's other thing. So that's why we are selecting GPU at the start itself. So model dot fit x train scale. So I hope you remember that we have scaled our data. So scaled data will many times give you better performance. So corresponding labels will be my y train, and I'll give this validation split. Should I give this validation? Okay, so I'll give this validation split as well. Split is equal to, let's take 10% of data, and epochs, let's have 10 epochs. So let's try to understand this. So I'm passing my images and the corresponding label. So the model will try to find the relationship between the labels, which is my y train, and the images. And validation split. So validation split is just like your test data, right? So when I say epochs is equal to 10, that means like my model will go through the data 10 times. So when I say epoch, it means one forward propagation and backward propagation. That means like your data goes through this neural network in forward, and it will also come back backward, and in this process your weights will get updated, right? And in each epoch 10% of data will be reserved as your test data, and at each epoch we will get our training accuracy and your validation accuracy. Okay, and later once this training is done, we can also evaluate our model with the test data that we have splitted using this train test bit. Okay, so let's run this. So this may take some time. Okay, so we are getting some error. So unknown loss function, sparse categorical cross entropy. So here I shouldn't mention a underscore, so that's the reason we are getting this error. So I'll run this. Now let's see. Yeah, it's working now. So this is the first epoch, and this is the steps that we have. So it seems this is not taking much time. You can see the accuracy value, loss function value. So loss function is nothing but the distance or the difference between your true value and your predicted value. So our goal is to minimize this loss function. So if your loss function minimizes, automatically your accuracy will increase. Okay, so we are starting from 29% accuracy, and we can see it's going up to 40% accuracy. Again, this is a very simple model. We don't even have convolutional layers to it. So convolutional neural network, which we call as CNN, works really well for image recognition problems. And I mean, in not all cases we would get a good model. Like, I mean, like, when I say good model, I mean, like, for most cases we can't build a accurate model, because like it's too hard for these models to capture this data. For this we use a technique called as transfer learning. Okay, because like in this case, if you see, we starting from this 29%, which is basically 30%, and in the third or fourth epoch itself, it's closing to 40% accuracy. But after 7 epochs there is no significant change, right? It's still at 40%, and the validation accuracy as well. So we use a technique called as transfer learning, where we take a pre-trained model which is already trained on a data set, and we use that model to train a similar data set. So we are not training it fresh, we are using the pre-trained model. We are training that on top of our own custom data set, as we have here the CIFAR 10 data set. And in those data sets would achieve better performance in a small number of epochs, and it's like always preferable. Like, that's what like we mostly use, because we can't build models from scratch all the time, because it takes a lot of resources and you need a lot of data which is not available all the time. So in this cases we move to this transfer learning techniques, where we have this open source ResNet50 and the other models. So there are like models like ResNet50, Inception, and other things. So you can search those things to get a better idea. So in this case, let's see how we can train a pre-trained ResNet50 model, and basically train it with the CIFAR 10, and get a better performance than this. So that's the idea of this particular video, as I've told you. Now let's go on to that important part of that video. So I'll create a text and I'll call this as ResNet50. And again, you will have different versions of these models. So we have to import this model first. So I'll import certain things. So from TensorFlow.keras, import sequential models and layers. So I mean, these layers are nothing but we have used keras.layers. So in this case, I'm just importing this layers directly from this TensorFlow.keras, and then we'll copy this from TensorFlow.keras import. So this probably won't change. From this, I'm going to import dense. So we have also built some dense layer in the above network that we have built. I'll also import this dropout. So I'll explain you what's the purpose of this dropout. Again, this is a very important thing. Flatten, as we already add, and from here I'm going to import my load model. Okay, okay, so load models should be in TensorFlow.keras. Okay. So from TensorFlow.keras.layers, we have to import this dense and drop. So these are like the different layers that we have, and load model should be imported from this load model from models. And there is another thing called as batch normalization from TensorFlow.keras.layers. So I'll explain you. Don't worry about all these things. So this may seem a bit complex, but these are pretty simple things. So I'll explain you while we are implementing this. So layers, let's import batch normalization. Yeah, batch normalization load model, and from TensorFlow.keras.model, import model with a capital M. Now let's import our ResNet model. So it's present in this from TensorFlow.keras.application. So there is another option, like from where you can import the pre-trained models, which is TensorFlow.app. For our dog versus cat classification, we have imported our mobile net model from TensorFlow app. You can also refer to it. So in this case, TensorFlow.keras.applications.ResNet50 import. So in this case, ResNet should be should be in lowercase, and here R and S should be, sorry, R and N should be in uppercase. ResNet50, and finally let's import our optimizers from TensorFlow.keras dot. Again, you have different optimizers. You can also search what are all the different optimizers that we have. Okay, I think this should be enough. Let's see. Invalid syntax. Yeah, my bad. Okay. No model name TensorFlow.keras.model. Okay, so this should be models. Okay, so first from this TensorFlow.keras we are importing the sequential. Sequential is nothing but we are going to stack all these layers within the sequential. So that's the purpose of this. We do this all the time. So models, layers. From this layers we are importing dense layer, dropout and flatten layer, and we are also from this layers we are importing this batch normalization, which is again a key thing. I'll explain you why this is used. We have also have this load model again for loading those models and just some small purposes. And then again this we have model from the same module of models, and from this TensorFlow.keras.applications.ResNet50 we are importing ResNet. This is the actual model that we are going to use. And finally we have optimizers from this TensorFlow.keras. Okay, so we have executed this. Now let's load the ResNet model. Okay, so I'm going to call this as convolutional base. So as I've told you, convolutional neural network is just similar to any other neural network. It's just similar to what we have here, but it just like additional layer called as convolutional layer. Like multiple convolutional layers can be there, and again you have this like pooling layer and so on. So let's discuss this in detail when we come to learn about this convolutional layers in a deep learning course, but just have this idea as of now. So in a CNN there are like apart from the input hidden and the hidden layer, we also have this convolutional layer. So these layers can capture the information in the image better. Right, so you can also like build convolutional neurals from scratch, and in this case we are not going to use this. So we are going to use the convolutional layer of ResNet50. So that's the purpose. So we'll create a variable as convolutional base. So this convolutional base is nothing but our ResNet50. I'll call this ResNet50, which we have imported from here, and within this I have to mention some parameters. Weight is equal to ImageNet, and include top is equal to false, and input shape is equal to 256 comma 256 comma 3. Now let's try to understand what these parameters mean. So we are creating a variable called as convolutional base, to which we are going to load this ResNet50. Weights is equal to ImageNet. So this ImageNet is nothing but it is a image data. It's like a image database where several like these models are trained. So this ImageNet data basically contains millions of images. I think it contains around 14 million images. If we want to train those images, I mean, you can think about the resource that it needs, which we can't actually do with our machines. So again, that's one thing. So when I say weights is equal to ImageNet, we are, when a ResNet model or any neural network or any model is trained based on this particular data set, it will derive some weights. Now I want to import the weights that the model has derived by training this ImageNet data. So I'll repeat this again. So when this ResNet50 model is trained on this ImageNet data, it gets some weights, and then we are going to retain those weights. And with our custom data set, we will train with this data, update few weights. So this is the process. So when I say weights is equal to ImageNet, it's basically the weights that are derived while training with this particular data. And now we have the include top is equal to false. So before going through this, I suggest you to just search about ImageNet and see what are all the different classes that we have, the number of images that we have. So this ImageNet data, I think it contains about thousands of classes, 1,000 classes or more than 1,000 classes. I'm not exactly sure. So in that case, your output layer may contain like, let's say 1,000 neurons, because it has to distinguish 1,000 different classes, right? Like something like that. But in this case, we don't have 1,000 classes. We just have 10 classes, right? So all those frog, bird, automobile, and those things, right? So when I say include top is equal to false, it will import the ResNet50 model, but it will drop the final layer, which is my output layer, and we just add our own output layer to this, because we know that we are not predicting 1,000 classes, we are just predicting for 10 classes. And other thing about transfer learning is you can't take some model and you can like train it with some data that is not related to it. Like ResNet50, this ImageNet is, this data is similar to what we have here. So we have some basic objects and animals, right? Frog, dog, and automobiles, and all these things are there. ImageNet also contains like those kind of images, so we can use this. Like if your model is trained on truck image and something like that, that can be used to predict car images. But you can't take a model that has been trained on truck and use it to predict dog or cat. So that won't work most of the times, right? So that's other thing. So there should be some similarity between the data that the original model has been trained on and the data that you're training. In this case, CIFAR10 is a bit similar to the ImageNet data, so we are using this. And as I've told you, include top is equal to false means we are not including the output layer. So this is very important. So we will add our own custom output layer with 10 neurons as we have seen before. And input shape is equal to 256, 256, 3. And this is again a key thing for you to remember. So this is nothing but the shape in which ResNet50 take the images, which is 256 width and 256 height, and 3, which is basically RGB images. Now our image, the CIFAR FAR dataset that we have, we know that it is not of this shape. This is 32 comma 32, right? And I have also told you this multiple times before that uh, you can train a neural network with images, but all these images should be of the same shape. And while predicting also, you should pass the image with the same shape. Like you cannot train a neural network with 256 comma 256 images and predict an image with 200 into 200 shape. So you have to rescale this to 256 comma 256. So this is how it works. But unfortunately in this case, we only have 32 comma 32 images and we don't have 256. So I'll show you how you can resolve this, but for now just have this idea. So first parameter is your weights, which is nothing but the data sets we mentioned it, so that it retains the weights of those weights it derived while training on that data set. Include top false, which means like we are not including the output layer. And input shape, the shape in which image ResNet50 expects the data to be, right? So and then I'll print this summary convolutional base dot summary. So it will just show you the different layers that this model has. So this will download this data. When you say this ResNet50, as you can see, it's download the neural network first, and this is the architecture of ResNet50. So I strongly suggest you just go to Google and search ResNet50 architecture. It will show you what's the input layer that you have. So as I've told you, these are some of the convolutional layers that we have. This is the pooling layer, right? So all these things. So again, we have this batch normalization. I'll explain you what this does and so on. So this is the architecture. This can be too much to look into as of now, but just search for uh, ResNet50 architecture and just have a look, right? You don't have to understand all these things right away. I'll explain you a few key things. So this is the architecture, right? So this is the convolutional base, which doesn't have that output layer, right? Okay, now we are going to add our own layers to this. So let's work on that aspect. So we are going to add some layers to this base, to this convolutional base, right? So I'll add this, create this same name as model. So model is equal to, I think you can use sequential. Let's use this models dot sequential. Okay, so previously we have used this models dot sequential. Within this parenthesis we have created a list and added all these layers. There is another way of doing this. So you can use this add function. So first I'm creating this models dot sequential, and I'm going to say model dot add. So from this also we can add layers to our neural network. Right, so this model is nothing but this one. So we are loading the sequential to this variable called as model, and first I'm going to add a upscaling layer. So layers dot upsampling, sorry, so upsampling 2D. I'll explain you what's the purpose of this. Just a sec. 2 comma 2. I'll copy this. Here you don't have to mention comma. So there we have mentioned this comma because within that sequential we have created this list. But we are just using this add function. You don't have to mention this comma. So I'll copy this 3 times. And model dot add convolutional base. So I'll explain you all these things. Don't worry. Just give me a moment. So convolutional base model.add layers.flatten. I think we have imported this flatten. We can use this directly or layers.flatten. I mean, both the things are same. And model.add is dot batch normalization. Okay, so make sure you mention this parenthesis here. So in flatten also we should have parenthesis. Okay, and then model.add layers dot dense. I think so. I mean, you don't have to mention the layers. I just want to have a uniformity. That's why, because we have already imported this dense, dropout, flatten, all these things. So you don't have to say layers dot batch normalization or layers dot flatten. So you can just say flatten, so it will work. So layers dot dense. Let's take 128 neurons. And activation, we are going to use relu as we have used before. Activation is equal to relu. And now I'm going to add a dropout layer. So model dot add layers dot dropout 0.5, and I'm going to add another batch normalization. Yeah, okay, after dropout, and I'm just going to repeat these steps. I'm just going to change the number of neurons as 64. I'm sorry, 64, 128, 64, and finally we can add a dense layer, basically your output layer, which should have 10 neurons as I've told you before. So here I'm going to, instead of 64, I'm going to say num of class. We have already created this variable, but just to avoid confusion, I'll create this variable again. Okay, number of classes is equal to 10. So first we have the sequential upscaling 3 times, convolutional base, and we have flatten, batch normalization, rectified linear units, dropout, again batch normalization, the 64 neurons, 0.5 batch normalization. Okay, now let's try to understand how we are setting up these layers. Okay, as I've told you, okay, so int object has no attribute, lower layers dot upscaling. Some issue that's happening. Int object data format is equal to value lower, int object has no attributes, layers dot model. So models dot sequential, model dot add layers dot upsampling. Okay, so I should put this in another parenthesis, so that's why. Okay, all right, yeah, this should probably work. Let's see. Okay, so let's run this. Yeah, it worked now. Okay, let's try to understand what's happening. So number of classes, we know we just have to mention the total number of classes that we have in our data set. Models are sequential, so in the within the sequential we are going to stack up all the layers. Now let's try to understand about this upsampling 2D. As I have told you, ResNet50 is probably trained on images that is of the shape 256, 256. In the previous case, if you have watched my dog versus cat classification, in that video, we have mentioned that we have to rescale the shape of the images to 224, 224, because in that case also we use transfer learning, but we use mobile net model. And the mobile net model is trained on images that are of the shape 224, 224, right? But in this case, we don't have that luxury to do that. We are not like, basically, I mean, we can do, but in this case, we are not rescaling the images while converting those to numpy arrays. But ResNet50 needs the images in the shape 256, 256. Three color channel is not an issue because we also have colored images. The ResNet50 also takes image as a colored image. Now, when I say model.add layers.upsampling 2D 2, 2, your height and width will be multiplied by 2 times. So it's basically like scaling up your image. Okay, so that is, it's like you're taking a 720p image and converting into 1080p image. So it's all about scaling. And 2, when I say 2, 2, 2 times of height and 2 times of width. And you can see I'm doing this 3 times, because when you multiply 32 by 2 one time, you will get 64. Again multiply this 64 by 2, you will get 128. Again multiply this 128 by 2, you will get 256. That's why we have this 3 layers. So before passing your images to your convolutional base, we have to make sure that we have upscaled our data to the shape of 256 comma 256. So the first thing is like scaling your data twice, which is it will become like 64 comma 64. Next time, once we do this step, your images will be of 128 comma 128, and after this process is done, your images will be of 256 comma 256. I mean the processed thing, not the base image. And then we are passing this to this convolutional base, which has all these layers as we have seen, right? And then we have this flatten. I've told you what's the purpose of this flatten. We just convert this matrix into a vector, so that all the values are in a form of a single column, right? So that's the main idea. So it's in the form of a single dimension. And then we have this batch normalization. So first we have to understand what is meant by normalization. In machine learning also, while doing feature scaling, we have discussed about this. We have two things called as normalization and standardization. So normalization is to make sure that all the values are of same range. If you have 10 columns in your data set, we have to make sure all the values are in the same range, right? So that's called as normalization. And we have already scaled our data. We know that all the values will be between 0 to 255, right? Strictly speaking, if you have scaled your data before, you don't have to use this batch normalization. But even though you scaled your data, if you use batch normalization, your training process is going to be efficient, your performance is going to increase, like most of the time. So what happens here in batch normalization is, so let's say we have an input layer and you have 3 hidden layers and you have a final output layer. So some processing is happening in your first hidden layer. So as I've told you, you have 3 hidden layers, and there are, like, let's say in the first hidden layer you have 10 neurons, and some processing happens here in this first hidden layer, and this first hidden layer will output, or will give this processed input to the second hidden layer, right? Now this batch normalization makes sure that all these values are of, all the values are normalized. So all this, so initially the image values that we are passing are normalized, basically they are scaled, but these processed values may not be normalized. So this is why we have this batch normalization at the end of each layer. So first we have this flatten layer, we are applying this batch normalization, and then we have our another dense layer. So as I've told you, we use values like 256, 128, 64 and 32, the powers of 2, so that it's efficient in terms of memory and computation. So here we have 128 and activation relu. So okay, so final case I'm going to softmax. As I've told you, for multi-class classification, most case we use softmax in the output layer. So let's come back to this. So we are adding this output layer with 128 neurons and activation of relu, and this dropout is a very important aspect. So neural networks are a very complex model and they have a tendency to overfit. So I hope at this point you know what is meant by overfitting. So overfitting is when your training data, your training accuracy is high but your test accuracy is very low. So there is like a huge difference between them. So that's called as overfitting. So that happens when your model cannot generalize generalize the data, generalize the modeling technique basically. So please, if you are not sure about this overfitting, please go through it. It is a very important concept in both machine learning as well as deep learning. And this dropout, what happens is, if there are like 128 neurons, it will turn off few neurons. So when I said turn off few neurons, it will basically give the output as 0, right? So some set of neurons should be turned off, and that how many neurons or how much of neurons should be turned off is determined by this value. So you can refer to what is meant by the 0.5, what happens when I mention 0.3 and all those things. So dropout is to turn off few neurons so that our model doesn't overfit. So this dropout is generally done to reduce the risk of overfitting. You can also train this without this dropout layer, but again you have this risk of getting a overfitted neural network. And again we are performing this batch normalization so that the output from this network is normalized. And then we are having another layer of hidden layers with 64 neurons, adding dropout to it, batch normalization. Finally we have our output layer. number of classes is 10 and activation is equal to softmax, right? I hope everything is clear. So this is actually much simple. Okay, and similarly, previously we have compiled and fitted our model, right? So we have to do the same. So I'll say model.compile. Just a moment. Okay, so model.compile, we have to add three things: optimizer, loss, and your metrics. So optimizer is equal to optimizer. So we have imported this optimizers. If you remember, we have imported this from, yeah, tensorflow.keras optimizers. So I'm not going to use Atom. I'm going to use a different optimizers called RMS prop. So I suggest you to check the different optimizers that you have and what they actually do. I mean, the concepts go much deeper. I don't want to go into these things as a, I mean, right away. So within this, I'll mention the learning rate as 2e power minus 5. So this basically learning rate determines how much your weights are going to change, right? So at each iteration, when your model learns from the data, it updates the weights, and learning rate determines how much change do we have to impart to that weight. So that's why we have this like learning rate. And I mean, if you remember gradient descent, it's similar to what's happening there as well. And the loss, again, it should be the sparse categorical cross entropy, because we didn't do one not encoding. If you did one not encoding, we use categorical cross entropy. So that's the difference. Sparse categorical cross entropy, yeah, so there shouldn't be a underscore there. So cross entropy. Next we have metrics. So metrics should be accuracy, as we have classification problem here. Okay, so let's run this. Yeah, model app compile. Now we have to fit our model, but before fitting, I'm going to fit it to a variable called as history. I'll explain you why I'm doing this after like this training is done. So model.fit xtrain scaled, comma, ytrain validation split. So I've already explained you what is meant by validation split. It's just like your test data, but the thing is it kind of like at each epoch it reserves some data as your test validation data, right? And validation split, I'm going to take 10% of this, and epochs, I'll give 10 epochs. So this will take so much time to train. I think it will take around an hour. So let's see. So history is equal to model.fit xtrain scaled ytrain validation split of 0.1 and epochs of 10. Okay, so let's run this, and this will carry out the training process, right? Okay, so let it run. In the meantime, I'll just like complete one last thing of plotting our loss and accuracy change. I mean, this is again a standard thing that we do in any neural network training. I'll load this history to a variable called as h, just like an abbreviation. And I think I've already imported matplotlib, right? Yeah, so we need matplotlib here. And first we are going to plot the loss function value, like how your loss value changes in 10 epochs first, and then we discuss like how our accuracy changes in the 10 epoch. So I'm going to say plt dot plot h dot history, sorry, so yeah, h dot history, we have loss. So we will print both, plot both validation loss as well as your train loss. The label is equal to training loss, and now we have to do this for validation loss. Val loss is nothing but your validation loss. Okay, and plt dot legend and plt dot show. And similarly, we have to plot our accuracy change as well. So basically we'll get two plots. Plot the accuracy value. So h dot history of ACC, this should be training accuracy, this should be your validation accuracy. So your accuracy should increase and your loss should decrease. So that's the idea. So should this be validation accuracy? Okay, so let me quickly check this. So PL H is equal to history, loss, training loss, validation loss. Okay, history. So this is just the label for our plot. So this is not important, but this shouldn't change. These four things shouldn't change. Okay. Okay. So again, as I've told you, this training will take around an hour. So I'll pause this video and I'll continue this once this training is done. Okay. So this training process almost took an hour. So you can see how much time this has taken. So it says like 52 minutes, and I think it took like a bit more time. So this is how we have fitted the data to this neural network. So we have fitted this scaled training data along with the training labels, and we have given validation split as 0.1, which is 10 percentage of this training data, and epochs is equal to 10. As we can see, the model has achieved good performance at the fifth epoch itself. So this is another reason that we go with transfer learning, so that we could achieve good performance with a lesser number of epochs, whereas previously with the model that we have built, so this is the performance that we got. So in the first 5 epochs we were able to achieve only 38 percentage starting from 29, whereas in this case with the ResNet50 that we have trained, so we have started with 46, and when we were able to increase the accuracy almost like 91%. And at the end of 10th epoch, so there were like almost 98% accurate with validation accuracy of almost 95, right? So you can change these things. So you can like I mean, you have to upscale the upsample this like 3 times. So similarly you can add a more dense layers to this, or you can try without a batch normalization, all these things. So try different activation functions maybe, so you would get like different results. So similarly like a different optimizer. So Adam, I think like Adam kind of gave a lower performance in this case, so you can like try different optimizers as well. So this is the final result that we are getting, and this is the evaluation of the model on the test data set. So you can see, so we are passing this X test scaled along with the testing data labels, and the accuracy is almost again 94 percentage, similar to what we got in this validation. So the change is not that much. So I mean, the model is definitely not overfitting, so we get a very good performing model with high accuracy. And as we have discussed before, we are plotting this history, so we are fitting this model dot fit to this history. From this only we will get this loss value, accuracy value, and so on. So we are plotting this h dot history, so we are just like renaming this. So when we say h dot history loss, it will take that loss value, and we say train loss, so you can see this legend that says train loss and validation loss. So we are mentioning the labels here. So we are plotting the loss for the training data and the validation loss. So the train data loss is represented as blue color, and validation loss is represented in this orange line. Okay, so you can see at a point like after this fifth or sixth epoch, there is not much difference in the loss. Similarly, it's like we don't have much change in the accuracy after this fifth epoch. So this is the result that we are getting. So if you want, you can also build a predictive system out of it. So take this trained model and just like build a predictive system where you can like pass in an image that belongs to those 10 classes and make the model to predict it. So you can like refer to the dog versus cat that we have seen. So the process would be a bit similar to that. So that's about it. I'll just give you a quick recap of what we have done from the start, so that it's a bit clear for you. So first we have just importing this library called Kaggle to load this data. Okay, one sec. So okay. So we are installing this Kaggle library, and as I've shown you, we need to import this, or we need to download this kaggle.json, and then like configure the path of this. Then we load this data directly from Kaggle to our collab environment through this Kaggle API, which is Kaggle competitions download CIFAR10. Like once we download this, we have extracting this zip file. Later we found that the file was a 7g compressed file, and for this we are using py7zr. So later, once we have extracting the train folder also, so once that has been run, we can see that these many number of files are there, which is 50,000. So after that we are processing this labels data frame, so we get to know that there are totally like 5,000 images that belongs to each of these class. And we know that there are like 10 classes, and then we are like numerically encoding each of these strings, which are nothing but our labels, right? So once that has been done, we are just like displaying few of the images. So we can see some frog and dog images there, and later we are like processing the image in the order of 1 to 50,000 in the order of this IDs. So like in this process we are reading the image in order, converting it to a numpy array, and storing it in a list which we will convert to a numpy array later, right? So you can see the first, this is the first image, so data of 0, and later like we are converting to numpy array here, x and y, where x is your numpy array of images and y is your numpy array of labels. And we can see the shape that it's 32,32 image with 3 channels, which is a colored image. And the next step is train test split with 20% test data, and then we are scaling the images, which is nothing but dividing it by 255 so that all the pixel values are between 0 and 1. So once that has been done, we are building a simple neural network with just one hidden layer, its softmax activation, and so on. So in this case we could see the performance, and later we are loading this ResNet50. So without this output layer, which is include top is equal to false, and the weights of image in a data set, and we are mentioning the input chip. So I've also clearly explained to you like what are all the different layers we are using here. So what is the purpose of these many upsampling, batch normalization, and so on. And then again we are compiling the model, fitting it, and later testing it with the test data, and finally building the plots of loss and accuracy. So I hope that you are clear with all the things covered in this video. So please practice this. So you can also try with different data sets that is similar to this data for object recognition with the same approach that we have done. Okay, so that's it from my side, and I'll see you in the next upload. Thanks for watching.